In this project, we will simulate the compressible flow over an airfoil in 3 dimensions. Now, as you know, the first step is to click on a fluid flow block and then drag it into the blank space inside Workbench software and then double click on Geometry section. Now, for the first step, we need to create the outline points of our airfoil. To do that, we click on Create and then select Point. On the low left side of the software window, in front of Type and Definition, make sure that Construction Point and From Coordinate files are selected. After that, on the coordinate files, we click on the None and select the files where the coordinates of the airfoil points are saved. It should only be pointed out that for those of you who have problem importing the coordinate points of the airfoil into the Design Builder software, please go back and watch session 3. After importing the coordinates of our airfoil points, we click on Generate button. Now that we have imported the outline points of our airfoil, it's time to import the outline curve of our airfoil too. To do that, we click on Concept and select 3D Curve. Just like what we did to import a point of our airfoil, we do the same thing here to import the curve too. Now, if we rotate the end of our airfoil and zoom a little bit in, we can see that the end of our airfoil is open. To close this open end, we need to create a point at the end and then connect it with the 2 other points. After selecting the point from the Create tab, this time in front of the Definition section, we need to select the manual input and then enter the coordinates of our point, as you will see in the next slides. Now that we've created our ending point, it's time to connect this point with the other 2 points using the Line from Points command. Now that we've created the outline of our airfoil, it's time to turn this outline into a surface. To do that, we click on Concept and then select Surface from Edges and then select 4 edges of our airfoil. Now our target here is to create another type of a structured mesh other than the mesh we created for the 3rd session. To do that, we click on Create and then go over Body Operation and then select Scale. After that, in the Tree Outline section, we select the outline body of our airfoil as the body we want to scale. In front of the scaling origin, we change it to body centroid, and then in front of the scaling type, we change it to non-uniform, and we set the value of x-axis scaling factor and y-axis scaling factor to the values you can see in the next slides. Now, when we select the body centroids option in the scaling origin section, the software will understand that we want to scale our geometry based on the center of our selected body. However, if we use the world origin, the software will scale the geometry based on the center of our coordinate system, which in this project would be the point placed on the left side of our airfoil. Now that we created this scaled line, it's time to change this line into a surface. To do that, we go over concept and then select surface from edges and then select the 4 edges that were created by scaling the outline of our airfoil. Now, in order to create the overall shape of our computational domain, we click on XY plane and then select the sketching button. In the tree outline section, we click on the sketching button, and then under the drawing section, we select the construction point. Now, after selecting construction point command, we need to create 3 points. The first point should be on the left side of our airfoil section, which is placed on the x-axis, and the other 2 points should be placed on the right side of our airfoil on the top and bottom of it. Now, in order to determine the spaces and distances between these 3 points, we click on dimensions and we select semi-automatic. After defining the dimensions for each of these 3 points, we can enter the value of dimensions for these 3 points on the lower left side of the software window under the dimensions section, and as you can see in the next slides. Now, after creating these 3 points, it's time to link these points using the line command. To do that, we click on draw and then select the line command and connect the 2 lines that are placed on the right side of our airfoil. Now, in order to connect the 2 points that are placed on the right side of our airfoil to the point that is placed on the left side, we select the spline command and connect these 3 points as you can see in the next slides. After connecting these 3 points using the spline command, the final step is to right click on the graphics window and then select the open end. Now that we created the outline shape of our computational domain, it's time to turn it into a surface. For this, we click on Concept, and then, this time, we select the Surface from Sketches button. Now it's time to separate the surfaces that we have created previously. To do that, we click on Create button and then go over Boolean. On the lower left side of the software window in front of the operation, we change it from unite to subtract. Now for the tool bodies, we select all the bodies that you can see in the graphics window by right-clicking on it and then select all the bodies. And for the target bodies, we select the outer surface as you can see in this slide. By doing this, the software will automatically understand that we want to subtract the inner surfaces from the outer surfaces. And also in front of the Preserve Tool Bodies section, we change this option from No to Yes, since we only want to separate these 2 surfaces and we don't want any of them to be deleted. In the previous step, we separated these two surfaces from each other. Now, in this step, we want to delete the first surface that we created using the outline profile of the airfoil. To do that, we again click on Create and then select Boolean. In order to make our job easier, we select the outer surface, right-click on it, and then select Hide Body. Now, just like what we did for the previous Boolean command, we select all the surfaces that you can see in the graphics window as the tool bodies, and as for the target bodies, we select the outer surface and we let the preserve tool bodies option to be no, meaning that we want to delete the middle surface. Now that we've deleted the unwanted surface, in order to show the hidden surface, we can simply right click on the graphics window and then click on Show All Bodies. Now it's time to divide these two surfaces into even smaller surfaces to be able to perform a structured mesh over them. The first step to divide these surfaces into smaller surfaces is to create different planes. After clicking on the New Plane button on the low left side of the software window in front of the type, we change it from plane to from point and normal. As for the base point, we select the ending point of the airfoil profile, which is placed on the right hand side of it, and as for the normal defined by, we select the x-axis as you can see in the graphics window. We also would like to rotate this plane around the x-axis. To do that, in front of the transform number 1, we change it from none to rotate around x-axis. And then in front of the FT1 value number 1, we enter the value of 5 degrees and then click on Generate button. We do the same thing again in order to create another plane, with the difference that this time we want to rotate our created plane about the x-axis with a value of minus 5 degrees. It should only be pointed out that this time, for the normal defined by section, we don't have any x-axis in the graphics window. Therefore, we can simply click the YZ plane, which has a normal vector parallel to the x-axis. Now the next two planes are to be created on the front side of our airfoil. To do that, we simply follow the exact steps which we had used to create the previous two planes. Now for the base point, imagine that we have divided our airfoil from the middle section into two parts of upper part and lower part. In the upper part, count and select the 7th point from the middle point, which is shown with the red line. Now this time, to rotate the created plane into our desired direction, we enter the value of FT1 value 1 equal to minus 30 degrees. And for the final plane, we follow the same steps that we have used to create the previous plane, with the difference that this time we enter the value of FT1 value 1 equal to 30 degrees. Now that we have all the needed planes, it's time to divide our geometry into different surfaces. To do that, we click on the Slice button. For the first slice, we will divide our generated surfaces into two parts, the upper part and the lower part. To do that, on the low left side of the software window in front of the base plane, we select the ZX plane and then click on Apply, and for the slice target, we let the option to be all bodies and then click on Generate. Now, before proceeding to the next step, it should be pointed out that after slicing the surfaces from the middle section, a very small line has been generated which should be merged with other lines. If you zoom a little bit and then rotate the intersection point of our two generated surfaces, there are two lines generated, which one of them is very small and unwanted. Now, to omit this unwanted line, we first have to hide the surfaces that are placed on the left side of our intersection point. After that, by using the merge command, we can merge these two lines and get rid of the unwanted line. Now you should pay attention that we need to do the same thing for the surfaces that are placed on the left side of the intersection point. To do that, we simply hide the faces that are placed on the right side of the intersection point, and then we merge these two lines that belong to the left surfaces. Now it's time to divide these generated surfaces into smaller surfaces by using the slice command and using the planes that we had previously created. To do that, we click on the Slice command and then select plane number 4 as the base plane, and in front of the Slice Target section, we change it from All Bodies to Selected Bodies, and then we select the two upper surfaces. And for the next slice command, we follow the same previous steps, with the difference that this time we select plane number 5 as the base plane, and in front of the slice target we again change it from all bodies to selected bodies, and we select the bottom surfaces. And for the next slice, we select plane number 6 as our base plane, and the rest is shown in next slides. And for the final slice, we follow the same steps that we used in previous slice commands, with the difference that this time we select the surfaces that are placed on the bottom side of our geometry. Now, if you pay attention, you can see that there are two triangular surfaces existing at the ending section of our airfoil. Now we are going to face problem when we want to perform a structured mesh over these surfaces. To solve this problem, we need to create another surface over these two surfaces. To create such surface, we need to first create 2 points on the right edge of our domain, so that using those 2 points we can create the outline of our surface. After clicking on the point command on the low left side of the software window in front of the type, we change it to construction point, and we change the definition format to manual input, and then we enter the coordinates of our desired points. After clicking on the point command on the low left side of the software window in front of the type, we change it to construction point, and we change the definition format to manual input, and then we enter the coordinates of our desired points. Now it's time to create the outline of our desired surface. To do that, we click on Concept and then select the Line from Points command, and then we link the points to each other, as you can see in next slides. After creating the outline of our desired surface, it's time to turn this outline into surface. To do that, we again click on Concept and then select the Surface from Edges and select the edges, as you can see in the next slides. It should only be pointed out that if you are facing problems selecting the line that is placed on the right edge of the geometry, you can simply click over it, and then on the low left side of the graphics window, you can simply click on each of the rectangles that are placed over each other until you find your desired edge. As you've probably guessed, now that we have created this surface is placed over the triangular faces that we want to omit and over the surface that are placed on the right side of our geometry. Therefore, we need to first hide this surface in order to omit the triangular faces, and next we need to subtract this generated surface from the two surfaces that are placed on the right side of our domain. To omit the triangular faces, we can simply select these two faces by holding down the Control key and then right-clicking over them and then selecting Suppress Body. Now that we have suppressed the triangular faces, it's time to subtract the created surface from the two previous surfaces that are placed on the right side of our domain. To do that, we click on Create and then select Boolean. After selecting the Boolean command on the low left side of the software window, in front of the operation we change it from unite to subtract, and then in front of the tool body we select the generated surface, And then in front of the target body, we select the two faces that are placed on the right side of our domain. We also change the Preserve Tool Bodies option to Yes. Now that we have created our desired surface, it's time to divide this surface into two parts of upper part and lower part, just like the first slice that we performed for our geometry. After selecting the slice command, we select the ZX plane as our base plane, and then under the slice target section, we change it from all bodies from the selected bodies, and we select our generated surface. Now that we have all the desired and divided surfaces, it's time to extrude them in order to obtain a 3D model. After clicking on the Extrude command button, we need to select the generated surfaces for the geometry that we want to extrude. We can simply click on Faces Selection, as you can see in this slide, and then go over a blank space in the graphics window, right click on it, and then click on Select All. After that, in front of the geometry, we click on Apply button, and in front of the operation, we change it from Add Material to Add Frozen. Then we click on Generate button. It should also be pointed out that in front of the direction vector section, we select the XY plane. Now, if you pay attention to the extruded surface near the ending point of the airfoil, you can see that there are two smaller extruded surfaces which are separated from the bigger surfaces related to the airfoil. Now, these separated and small surfaces should be merged with the bigger surfaces. To do that, we select, for example, the bottom surfaces of the airfoil, and then go over Tools and then select Merge command. In front of the Faces section, we click on Apply button, and in front of the Merge Boundary Edges, we change it from No to Yes. And then we click on Generate button. We also follow the same previous steps for the upper surfaces of the airfoil. Now it's time to suppress the bodies that we don't want anymore. To do that, we can simply right click on each of these bodies and then click on Suppress Body, as you can see in the next slide. After suppressing the unwanted bodies, we need to turn these separated solid into one part. To do that, we can simply select all the solid bodies and then right click over them and then select Form New Part. We also change its type from solid to fluid, and then we can save our project and close the design modeler software. After creating the geometry, it's time to generate mesh over it. To do that, we double click on the mesh. In the ANSYS meshing software, the first thing we need to do is to name our boundaries. To do that, we click on the face selecting button and then select all the faces that are placed on the side of our geometry and name them as pressure far field, as you can see in the next slides. After selecting these faces, in order to give a name to them, we right click on them and then select Create Name Selection, and then in the appeared window we type Pressure Far Field. After that, we select all the faces that exist on two sides of our geometry and we create name for them as symmetry boundary. Next, we select the inner bottom wall of the airfoil face and we create name for it as bottom wall. We do the same thing for the upper airfoil wall and set its name to top wall. And finally, we select the body selection button and we select all the bodies in our geometry and name them as flows so that the software will understand that a fluid flow will pass through these bodies. Now, in order to create a boundary layer mesh, we select all the edges as you can see in the next slide and then give them the needed setting in order to create a boundary layer mesh. After selecting all the edges that are needed, we right click on them and then go over Insert and select Sizing. After that, on the low left side of the software window in front of the type, we change it from element size to number of division and we set the number of division to 80. Also, we change the behavior from soft to hard. Now, in front of the bias type, we select, for example, the first bias type, and then in front of the bias option, we select smooth transition and we set its value to 1.09. After defining the bias type and bias option, you need to make sure that the smaller mesh cells are placed near the airfoil boundary. If there is an edge that has a wrong mesh cell direction, you can choose and select the reverse bias option, and then by just clicking on that edge, you can change the direction of mesh cells over that edge. Now the next sizing setting is for the edges that are placed in the front section of our airfoil. Just like the previous slide, we click on those edges and then right click over them and then go over insert and select sizing. On the low left side of the software window, in front of the type, we change it from element size to number of divisions, and then beneath it, we enter the value of 20. We also change the behavior from soft to hard, just like the previous edges. Next, in front of the bias type, we select the first type, and if we enter the value of bias factor to 4, we also make sure that the smaller mesh cells are placed at the tip of our airfoil edge. Next, we select the edges as you can see in this slide and next slide. Then in front of the type, we change it to number of division, and then we enter the value of 20. We also change the behavior from soft to hard. For the next sizing, we select the edges that are placed on the top and bottom side of our airfoil, and we right click on them and we go over insert and select sizing. Again, on the low left side of the software window in front of the type, we change it to number of division and we enter the value of 80. We also change the behavior to hard. Then in front of the bias type, we select a type where it has bigger mesh cells at the center of our edge and smaller mesh cells on the end. We also enter the value of bias factor equal to 6. Next, we select the upper and bottom edges of the previous edges and then right click on them and then go over insert and select sizing. In front of the type, we change it from element size to number of division and we enter the value of 80. We also change the behavior just like the previous edges from soft to hard. Next, in front of the bias type, we select the type where it has a smaller mesh cells at the left side of these edges. And then we enter the value of bias factor equal to 2. Next, we select the outer edges that are placed on the left side of our domain, and just like the previous edges, we select a sizing method for them. Next, on the low left side of the software window, we change the type from element size to number of division, and we enter the value of it equal to 20. We also change the behavior from soft to hard. Next, in front of the bias type, we select the first type and we make sure that the direction of mesh cells is in a way where we have smaller mesh cells at the intersection points between these two edges. And we enter the value of bias factor to 6. Next we select the edges as you can see in this slide and next slide, and then we give them sizing method. We follow the same previous steps here as well, and we enter the value of number of division over these edges to 80. For the next sizing method, we select these three edges as you can see in this slide and next slide. Then we right click over them and then go over insert and select sizing. Just like the previous sizing settings, we change the type from element size to number of division, and we enter the value of number of divisions over these cells equal to 100, and we change the behavior from soft to hard. In front of the bias type, we select the first type and we change the bias option from bias factor to smooth transition, and we enter its value to 1.04, and we make sure that we have a smaller mesh cells at the tail section of the airfoil. As you can see in this slide, the direction of mesh cells at these two edges need to be changed. Therefore, we select the reverse bias option and then we select these two edges. Next, we select the edges that are placed on top and bottom side of these three edges, and just like the previous slide, we right click over them and then go over insert and select sizing. On the low left side of the software window, in front of the type, we change it from element size to number of divisions, and then we enter the value of number of divisions equal to 100. We also change the behavior from soft to hard. Next, we select these two small edges that are placed on the right side of our domain, and we right click over them and then go over insert and select sizing. Again, just like the previous edges, in front of the type, we change it from element size to number of division, and we enter the number of divisions equal to 80, and we change the behavior to hard. And for the final edge sizing, while holding down the control key, we select these edges as you can see in the next slide. Then we right click over one of them and then go over insert and select sizing. Then in front of the type, we change it from element size to number of divisions, and we enter the number of divisions over these edges equal to 50. We also change the behavior from soft to hard. Now over these edges, we want the mesh cell direction to be in a way which we have a smaller mesh cells near the airfoil geometry. To do that, in front of the bias type, we select the first bias type, and then in front of the bias factor, we change it to a smooth transition, and we enter the value of growth rate equal to 1.08. Now in this slide you can see that some of the mesh cell direction over these edges do not have the preferred direction. We can change the direction over these edges by using the reverse bias option. Now that we've created edge sizing for all of the edges over the face of the geometry, as you can see in this slide, it's time to use the sweep method in order to transmit the edge sizing that we've created for this face in the depth of our geometry. To enable this option, we right-click over the mesh, go over Insert, and select Method. Now on the low left side of the software window, as you can see, the software asks us for a geometry where we want to perform this sweep method. To introduce the whole geometry, we can simply right-click in the blank space and then go over Select All option. Next, in front of the geometry, we click on Apply button, and then in front of the method, we change it from automatic to sweep. Then in front of the SRC or TRG selection, we change it from automatic to manual source, and then we select the face where we had created edge sizings previously on it. Then in front of the source, you can see the software asks us for a face source. Therefore, we select the face where we had created the edge sizings over it. Then in front of the free face mesh type, we change it to all quad since we want to create quadrilateral mesh in the depth of our geometry as well. We also change the sweep number division to 10, and then we click on Generate button. Now as you can see, our work in ANSYS meshing software is finished, therefore we can close the ANSYS meshing software. Now after generating mesh for our model, we double click on the Setup button in order to launch the Fluent software. In the appeared window, we enable the double precision option, and in front of the solver processes, you can enter the number of CPU cores you want to use in your simulation process. By clicking on Check button, you will see that under the Console tab, the Fluent software will start to check your mesh for any errors. Also by clicking on Report Quality, again in the Console tab, the Fluent software will give you the quality report for your mesh. For example, you can see the maximum aspect ratio of your mesh, maximum orthogonal quality, and etc. Now, since we are going to investigate the compressible flow over our airfoil, under the solver section, we change the type of solver from pressure-based to density-based. By doing this, we add the density as a variable in our equations, which can be calculated using the ideal gas law. The other assumptions in this project are as follows. The velocity formulation is taken to be in absolute format, and as for the time study, we have selected the steady time study since we didn't want our results to be a function of time. Under the model section, if you double click on the energy button, in the appeared box you can see we have enabled the energy equation since we wanted to calculate the temperature changes in order to use them inside the ideal gas law to calculate the density changes. Next, if you double click on the viscous button in the appeared window, you can see we have selected the Spalart Almaros model since this model yields pretty good results for the compressible flows. Now, after expanding the fluid under the material section and double-clicking on that material in the appeared window under the properties, we have to change the density from constant to ideal gas. We also would like to calculate the changes in viscosity due to the temperature change using the Sutherland model. After selecting the Sutherland model in the appeared window, you can see we have selected the 3-coefficient method with the coefficients that you can see beneath it. Also, you can see the formula of the 3-coefficient method Sutherland model in this slide as well. After changing the needed settings, we click on Change and Create, then close this window. The next task is to change the reference pressure value in the operating conditions section. To do that, we expand the cells and condition and then double-click on the Flow button. After clicking on the Operation Condition button, a new window will appear. In the appeared window, you can see we have changed the operating pressure value to 0 Pascal. It should be pointed out that for compressible flows, the solver needs to use the absolute values in the calculation. Therefore, it is sometimes convenient to set the operating pressure to 0. However, this is simply a user preference, meaning that you can keep the previous reference pressure value and don't change it. Now, if you click on the inlet boundary or the pressure far field, you can see the type is defined as pressure far field as well. By clicking on Edit button, a new window will appear in which you can change the settings for this boundary. In the appeared window under the Momentum tab, in front of the gauge pressure, enter the value of 73,048 Pascal, which is calculated using the formula shown in this slide. And in front of the Mach number, we enter the value of 0.7. And then, since we want to apply an angle of attack equal to 1.53 degrees for our airfoil, in front of the X component and Y component of flow direction, we enter the values of cosinus and sinus of 1.53 degrees respectively. Next, under the Turbulence section, we change the specification method from turbulent viscosity to intensity and length scale. And then we enter the value of turbulent intensity and turbulent length scale equal to 0.01 and 0.02 respectively based on the experimental data. The next step is to click on the Thermal tab and set the right temperature for the pressure far field boundary using the formula which is shown in this slide. Also, for the wall boundaries, all you have to do is to click on each of them and then click on Edit button. In the appeared window, you can see the stationary wall motion along with no slip shear condition are defined for these walls. Also, if you click on the Thermal tab, you can see the heat flux thermal condition is defined and the value of heat flux applied on these walls is equal to 0, meaning that these walls are adiabatic. Now, for the next step, we have to double-click on the Reference Values button and correct these values. We can simply do that by clicking on the Combo Down list under the Compute Theorem and then select the Pressure Far Field boundary. The most important values in this list are the area and length, which are used to calculate the parameters like pressure coefficient, which we will be extracting at the end of this project when the solution is completed. The CFD model itself is now defined, but the solver settings need to be modified. By double-clicking on the Methods button, in the appeared part under the Solution method, you can see we have selected the implicit formulation and ROEFTS flux type. Also, under the Spatial Discretization, we changed the modified turbulent viscosity from first order of wind to second order of wind in order to increase the accuracy of our calculations. We also uncheck the pseudo-transient option since we want to calculate our solution in a complete steady form. After double-clicking on the Controls button, in the Appeared part you can see different parameters like current number and under-relaxation factors. The current number, or CFL, determines the internal time step and affects the solution speed and stability. In other words, the CFL determines how fast we are progressing in our simulation process. In this section, we enter the value of current number equal to 2.5. However, it is often possible to increase the CFL to 10, 20, or even 100, depending on the stability of the solution. It may be that a lower CFL is required during the startup, but it can be increased as the solution progresses. We also leave the values of under-relaxation factors unchanged. There are two ways to check that your simulation process have reached convergence. Alongside the checking the residuals reaching and nearing zero, you may define some report to make sure that an equation have reached convergence. For example, by just right-clicking on the report definition, going on the new, you are able to choose between different reports. For example, you can define a mass flow rate report on an arbitrary boundary based on your geometry and your simulation. You are able to see whether this mass flow has reached a constant value or not. If yes, it may be a sign that your simulation has reached convergence, but the residual must be checked as well. For example, in this project, we are going to define a drag report over the airfoil wall boundaries in order to monitor the changes of drag force as our simulation progresses. In the appeared part, the first thing we can do is to change the report name. The next task is to define the force vector. Now, as we all know, the drag force has the same direction as the flow. Therefore, we have to change the values of x and y force vectors using the cosinus and sinus of the angle of attack. We also enable the options of report file and report plot so that the values in this report will be shown and saved at the same time for us. And finally, under the wall zone section, we select both walls, which relates to the airfoil walls, and then click on OK button. After double-clicking on the Residuals button, a new window will appear. In the Appeared window, you can see the absolute criteria for equations like continuity, x velocity, y velocity, and so on. Now, when you set the software to start the simulation, there would be error between each iteration. Now, if that error is less than these criterion, it conveys the meaning that that equation has reached convergence. However, in this project, we uncheck the check convergence option for all of the parameters since we want the software to finish the desired number of iteration for us. After double-clicking on the initialization button, a new window will appear showing you different methods of initialization, hybrid and standard. Now in the standard initialization method, you get to choose the first amounts and values for the first iteration of the simulation progress. These values refers to the values used in the first iteration of the simulation progress, and if you choose the values for each parameter wisely, your simulation progress will finish sooner. It should be mentioned that you can also choose the first values or the initial values by just clicking on the Compute From drop-down list and clicking on one boundary. For example, by clicking on Compute From All Zones, the software will automatically average the values in different zones and boundaries and put those values in the initial values for the software. For example, in this project, we select the pressure far field boundary under the Compute From section and then click on Initialize button. After the initialization process, we double-click on the Run Calculations button, and in the Appeared part, under the Parameter section, we enter the value of number of iteration we want the simulation software to calculate our solution equal to 5,000. Now, as you can probably remember, when we talked about the CFL or current number, we said that we need to define a small value for it at the startup section of our simulation process, and that we can change this value as the simulation progresses. Now there are two options available for us to change the value of current number as the simulation progresses. The first option is to do that manually, meaning that we can stop the simulation process, change the value of CFL, and then continue solving the solution. Or we can enable the solution steering option and let the software do this automatically. After enabling the solution steering option under the flow type, we change it from Subsonic to Transonic. And then, by clicking on the More Settings button, a new window will appear. In the appeared window, under the Settings tab, under the current number section, you can see we have defined the initial and maximum values of the current number. For the initial value, we enter the value of 2.5 and we leave the maximum value unchanged. We also change the explicit under relaxation factor from 0.75 to 0.5 in order to increase the stability of our solution. It should only be pointed out that defining a big number for the maximum value of the current number may increase the errors in our results. However, in this project, since we wanted to finish our calculations sooner, we set the maximum value of the current number to 200. After defining the needed settings, we click on Calculate button and the software will start the simulation process. Now after some time, when you check the scale residuals and drag report that we had defined, you will see that the residuals and the value of the drag force have reached a constant value, meaning that our solution is probably converged. Therefore, we can stop the calculations. Now, in order to create a pressure coefficient diagram over the airfoil walls, we need to create two lines over the top and bottom wall of our airfoil. To do that, we right-click the surfaces, go over New, and then select Isosurfaces. In the appeared window, under the surface of constant, we select Mesh, and underneath it, we select Z-coordinate. After that, we click on Compute button, so that the software will calculate the extents of our geometry in Z direction. After that, we enter the value of ISO values so that our surface will be created in the middle section of our geometry. Now that we've created a surface in the middle section of our geometry, we need to calculate its intersection with the bottom and top wall of our airfoil so that we have a line on the top airfoil wall and a line on the bottom wall of the airfoil. To do that, we simply change the new surface name to Z-line bottom, and then under the surfaces section, we select the bottom wall of our airfoil and then click on Create button. We do the same thing to create the upper line, with the difference that this time, in the From Surfaces section, we select the top wall of our airfoil and then click on Create button. Now, in order to view these created lines, all you have to do is to expand the Graphics section and double-click on the Mesh button. In the appeared window under the Surfaces section, if you select these four walls and then click on Save or Display button, you can see the airfoil walls and the lines that are created over them. Now, in order to extract the pressure coefficient diagram, we expand the plots and then double-click on XY plot. In the appeared window, under the y-axis function, we select pressure and underneath it, we select pressure coefficient. And under the surfaces section, we select two lines that we had previously created. And in this slide, you can easily see the pressure coefficient values over two lines that we have created on the airfoil surface. We can also extract different contours on the middle section plane that we have created by simply right-clicking on Contours button and then go over and selecting New button. In the appeared window, for example, in order to extract the Mach number contour, you can change the pressure to velocity and then underneath it, selecting the Mach number and then selecting the Z coordinate number 4, which is the plane that is generated in the middle section of our geometry, and then clicking on Save or Display button.
To benefit from Mr. CFD services including simulation, consultation, and training, contact our experts via info@mrcfd.com.